An isolated grounding conductor is considered an equipment grounding conductor. According to the National Electrical Code, or NEC, Section 250.119, equipment grounding conductors shall be identified by one of the following means: firstly, green or green with one or more yellow stripes; secondly, bare copper wire; or thirdly, other approved means. Since an isolated grounding conductor is an equipment grounding conductor, it must follow the same color code requirements as other equipment grounding conductors. Considering a multi-conductor cable in a tray cable system that uses green for the equipment grounding conductor and orange for the isolated grounding conductor, this is acceptable according to NEC 250.119T, which allows orange to be used as an isolated grounding conductor. Therefore, there is no need to re-identify the orange conductor. To summarize, an isolated grounding conductor is an equipment grounding conductor and must follow the color code requirements of NEC Section 250.119. The use of orange for the isolated grounding conductor is acceptable in the scenario described. The isolated grounding conductor, often referred to as an IGC, serves a specific purpose within electrical systems. It's designed to minimize electrical noise and interference in sensitive electronic equipment. Unlike standard equipment grounding conductors, the IGC is intentionally isolated from the metallic enclosures and raceways of the electrical system. This isolation helps prevent circulating currents, which can induce unwanted signals in sensitive equipment. The NEC provides guidelines for the proper installation and identification of IGC to ensure safety and effectiveness. The equipment grounding conductor, or EG, on the other hand, provides a low impedance path for fault current to return to the source. This path facilitates the operation of overcurrent protective devices, such as circuit breakers and fuses, in the event of a ground fault. The EGC is bonded to the metallic enclosures and raceways of the electrical system, creating a continuous ground path. Proper grounding is essential for electrical safety, as it helps to prevent electric shock and minimize the risk of fire. The color code requirements for grounding conductors are specified in NEC Section 250.119. This section mandates that equipment grounding conductors be identified by green or green with one or more yellow stripes. This color coding helps to ensure that grounding conductors are easily identifiable and distinguishable from other conductors in the electrical system. The use of consistent color coding practices is crucial for maintaining electrical safety and preventing accidental miswiring. In the case of isolated grounding conductors, the NEC permits the use of orange as an alternative color. This allowance is specifically outlined in NEC Section 250.119D, which states that orange may be used to identify IGC. The use of orange helps to differentiate IGC from standard equipment grounding conductors, which are required to be green or green with yellow stripes. When installing an electrical system with both equipment grounding conductors and isolated grounding conductors, it's important to follow the NEC guidelines for color coding and identification. This will help to ensure that the system is safe, reliable, and easy to maintain. In summary, the NEC defines an isolated grounding conductor as a type of equipment grounding conductor with specific requirements for isolation and color coding. The use of orange is permitted for IGC, while green or green with yellow stripes is required for standard equipment grounding conductors. Proper grounding practices are essential for electrical safety and should be followed at all times. NEC Section 250.119D allows for the use of orange for isolated grounding conductors, but it's important to understand the specific requirements and limitations associated with this allowance. The orange conductor must be used exclusively for the IGC and must be properly identified at all termination points. Additionally, the IGC must be insulated along its entire length, except where it's connected to the equipment it serves. When using orange for an IGC, it's important to ensure that all electrical personnel are aware of the color code and its significance. Proper training and communication can help to prevent accidental miswiring and ensure the safety of the electrical system. In addition to the color code requirements, the NEC also specifies requirements for the size and ampacity of grounding conductors. The size of the grounding conductor must be sufficient to safely carry the maximum fault current that could occur in the electrical system. The ampacity of the grounding conductor must also be adequate to prevent overheating and damage to the conductor. NEC Table 250.122 provides guidance on the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device. This table should be consulted to ensure that the grounding conductor is properly sized for the application. When installing grounding conductors, it's important to follow the manufacturer's instructions and the NEC guidelines for termination and bonding. Grounding conductors must be securely connected to the equipment and the grounding system to ensure a low impedance path for fault current. Proper bonding techniques such as using listed connectors and applying antioxidant compounds can help to prevent corrosion and maintain a reliable ground connection. The integrity of the grounding system should be periodically inspected and tested to ensure that it's functioning properly. Ground resistance testing can be used to verify that the grounding system provides a low impedance path to ground. Visual inspections can also help to identify any signs of damage, corrosion, or loose connections. Any deficiencies in the grounding system should be promptly corrected to maintain electrical safety and reliability. In addition to the NEC requirements, there may be local codes and regulations that apply to grounding systems. It's important to consult with the local electrical inspector to ensure that the installation complies with all applicable requirements. The electrical inspector can provide guidance on specific grounding requirements and help to ensure that the installation is safe and code compliant. In summary, grounding is a critical aspect of electrical safety and should be given careful consideration during the design, installation, and maintenance of electrical systems. The NEC provides comprehensive guidelines for grounding, including requirements for color coding, sizing, termination, and testing. By following these guidelines and consulting with qualified electrical professionals, it's possible to ensure that electrical systems are properly grounded and safe for use. It is very important to remember that electrical codes can change frequently as updates are published every 3 years and best practices adapt to new technology. Always check with your local authority having jurisdiction, such as the city or state electrical inspector's office, as well as consulting the most recent version of the NEC before starting any electrical work. The NEC is not a step-by-step instruction manual and requires a qualified person to design and install electrical systems. The NEC contains tables that help determine the correct wire size, conduit fill, and breaker size for an electrical circuit. For example, NEC Table 310.16 provides ampacity ratings for various conductors based on their insulation type and ambient temperature. This table is used to determine the appropriate wire size for a given load. NEC Chapter 9 contains examples of how to calculate branch circuit, feeder and service loads for residential and commercial buildings. These calculations are used to determine the size of the electrical service and the capacity of the distribution equipment. NEC Article 250 covers the requirements for grounding and bonding electrical systems. This article specifies the types of grounding electrodes that are permitted, the methods for connecting grounding conductors, and the requirements for bonding metal enclosures. NEC Article 300 contains general requirements for wiring methods. This article covers topics such as cable support, protection against physical damage, and the installation of wiring in damp or wet locations. NEC Article 310 covers the requirements for conductors for general wiring. This article specifies the types of conductors that are permitted, the ampacity ratings of conductors, and the requirements for conductor identification. NEC Article 400 covers the requirements for flexible cords and cables. This article specifies the types of flexible cords and cables that are permitted, the uses of flexible cords and cables, and the requirements for connecting flexible cords and cables. NEC Article 408 covers the requirements for switchboards and panel boards. This article specifies the types of switchboards and panel boards that are permitted, the construction requirements for switchboards and panel boards, and the requirements for overcurrent protection. NEC Article 430 covers the requirements for motors, motor circuits, and controllers. This article specifies the types of motors that are permitted, the requirements for motor circuit protection, and the requirements for motor control. NEC Article 440 covers the requirements for air conditioning and refrigerating equipment. This article specifies the types of air conditioning and refrigerating equipment that are permitted, the requirements for circuit protection, and the requirements for disconnecting means. NEC Article 500 through 516 covers the requirements for hazardous classified locations. These articles specify the types of hazardous locations, the classes and divisions of hazardous locations, and the requirements for electrical equipment in hazardous locations. NEC Article 600 covers the requirements for electric signs and outline lighting. This article specifies the types of signs and outline lighting that are permitted, the requirements for circuit protection, and the requirements for disconnecting means. NEC Article 625 covers the requirements for electric vehicle charging systems. This article specifies the types of electric vehicle charging systems that are permitted, the requirements for circuit protection, and the requirements for disconnecting means. NEC Article 680 covers the requirements for swimming pools, fountains, and similar installations. This article specifies the types of swimming pools, fountains, and similar installations that are permitted, the requirements for bonding and grounding, and the requirements for ground fault circuit interrupter protection. NEC Article 690 covers the requirements for solar photovoltaic systems. This article specifies the types of solar photovoltaic systems that are permitted, the requirements for circuit protection, and the requirements for disconnecting means. These are just a few examples of the many topics covered in the NEC. It is important to consult the NEC and other applicable codes and standards to ensure that electrical installations are safe and code compliant. Proper grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to return to the source, which helps to trip the overcurrent protective device and prevent electrical shock. Bonding connects metal parts of the electrical system together to create a low impedance path for fault current. The NEC specifies the requirements for grounding and bonding in Article 250. The NEC requires that all metal enclosures containing electrical conductors be grounded. This includes metal conduits, metal boxes, and metal equipment enclosures. The grounding conductor must be sized according to NEC Table 250.122, based on the rating of the overcurrent protective device. The NEC also requires that all metal water piping systems be bonded to the electrical grounding system. This helps to prevent electrical shock in the event of a ground fault. The bonding conductor must be sized according to NEC Table 250.66, based on the size of the service entrance conductors. The NEC requires that ground fault circuit interrupters, or GFCIs, be installed in certain locations such as bathrooms, kitchens, and outdoor areas. GFCIs protect against electrical shock by detecting small ground faults and tripping the circuit. The NEC specifies the locations where GFCIs are required in Article 210.8. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning or other events. The NEC recommends that SPD be installed in all electrical systems. The NEC specifies the requirements for SPD in Article 280. Electrical safety is a very important consideration when working with electricity. Always follow safe work practices and use appropriate personal protective equipment, or PPE. Before working on any electrical equipment, always de-energize the circuit and verify that it is de-energized with a voltage tester. Never work on live electrical equipment unless it is absolutely necessary. Wear appropriate PPE, such as rubber gloves and safety glasses, when working with electricity. Be aware of the potential hazards of electricity, such as electrical shock, arc flash, and arc blast. Follow safe work practices to minimize the risk of injury. The NEC is a comprehensive code that covers all aspects of electrical safety. By following the NEC and other applicable codes and standards, it is possible to ensure that electrical installations are safe and code compliant. Always consult with a qualified electrician or electrical engineer before starting any electrical work. The National Electrical Code, or NEC, serves as the cornerstone for safe electrical installations. It's important to understand that the NEC is not a design manual, but rather a set of minimum requirements intended to protect people and property from electrical hazards. The NEC is updated every 3 years, reflecting advancements in technology and evolving safety practices. Local jurisdictions often adopt the NEC, sometimes with amendments to address specific regional needs. Therefore, it's crucial to consult the latest edition of the NEC and any applicable local codes before undertaking any electrical work. The NEC is organized into chapters, articles, and sections, each addressing specific aspects of electrical systems. Chapter 1 covers general requirements, including definitions, wiring methods, and grounding principles. Chapters 2, 3, and 4 delve into wiring and protection, wiring methods and materials, and equipment for general use, respectively. Chapters 5, 6, and 7 address special occupancies, special equipment, and special conditions, encompassing a wide range of unique electrical environments. Finally, Chapter 8 focuses on communication systems such as telephone, cable television, and data networks. Within each chapter, articles provide more detailed guidance on specific topics. For example, Article 210 covers branch circuits, Article 250 covers grounding and bonding, and Article 300 covers wiring methods. Sections within each article offer specific requirements and recommendations, often referencing tables and examples to illustrate proper application. Understanding the NEC structure and organization is essential for navigating the code and finding relevant information quickly. The NEC relies heavily on tables to provide practical guidance on conductor sizing, conduit fill, overcurrent protection, and other critical aspects of electrical installations. These tables are based on extensive testing and engineering analysis, ensuring that electrical systems are designed and installed safely and effectively. For example, Table 310.16 provides ampacity ratings for conductors based on their insulation type, ambient temperature, and installation conditions. This table is used to determine the appropriate wire size for a given load, taking into account factors such as heat dissipation and voltage drop. Other important tables include Table 220.42, which provides demand factors for various types of loads, and Table 250.122, which specifies the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device. Using these tables correctly is crucial for ensuring that electrical systems are properly sized and protected. The NEC also includes numerous examples to illustrate the application of code requirements in real-world scenarios. These examples help clarify complex concepts and provide practical guidance on how to comply with the code. For example, the NEC provides examples of how to calculate branch circuit loads, feeder loads, and service loads for residential and commercial buildings. These examples demonstrate how to apply the demand factors and other requirements specified in Article 220. Other examples illustrate how to properly ground and bond electrical systems, how to install wiring in hazardous locations, and how to comply with the requirements for special equipment such as swimming pools and electric vehicle charging stations. Studying these examples can greatly enhance understanding of the NEC and improve the quality of electrical installations. In addition to the NEC, other codes and standards may apply to electrical installations depending on the specific location and type of project. These may include local building codes, fire codes, and accessibility standards. It's important to consult with the local authorities having jurisdiction to determine which codes and standards apply to a particular project. Compliance with all applicable codes and standards is essential for ensuring the safety and legality of electrical installation. Furthermore, industry standards developed by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA, provide valuable guidance on specific electrical topics. These standards cover a wide range of subjects, including power quality, grounding and bonding, and electrical safety in the workplace. Consulting these standards can help to improve the design, installation, and maintenance of electrical systems. The NEC is a complex and ever-evolving document, requiring ongoing education and training to stay up to date. Electrical professionals should participate in continuing education courses, attend industry conferences, and subscribe to relevant publications to stay informed about the latest code changes and best practices. The NEC is updated every 3 years, and each edition includes significant revisions and additions. Staying current with these changes is essential for ensuring compliance with the code and maintaining a high level of electrical safety. Furthermore, electrical professionals should seek certifications from reputable organizations such as the National Electrical Testing Association, or NETA, and the International Association of Electrical Inspectors, or IE. These certifications demonstrate competency and commitment to professional development. Finally, it's important to remember that the NEC is not a substitute for sound engineering judgment and experience. The electrical installations should be designed and installed by qualified professionals who have a thorough understanding of electrical principles and safety practices. The NEC provides a framework for safe electrical installations, but it's up to the professionals to apply the code in a responsible and ethical manner. The goal is to create electrical systems that are not only code compliant but also safe, reliable, and efficient.